Good afternoon.
No, that's not right. Yes, no, that's right. That's right.
Well, welcome to this part of the seminar series. For those that don't know me, Shachak. I don't need introductions, making too much noise anyway. And originally, when I registered for the CCOM Seminar Series, we had a different project in mind that was talking about sensors, because typically what I research is the capability, limitation, and potential of different optical sensors. And we wanted to talk about the system. We had some issues about the name. That was a big issue, so we couldn't consider what to do here. And one lucky thing is we had a different project coming on. So as I said before, I'm focusing mostly on optic sensors. And for those that are not familiar, this is what we call a camera. Now, this camera is actually quite unique. It's from 1903. It was used in Germany. And what they had been so much excited about is the platform they can put this camera on. And that's actually where I was introduced quite intimately to the capabilities of mechanical engineering. So, because when I think about platforms, I don't really care. It can be any platform I can think about. And it was quite interesting. A platform that can be also dinner. What's better than that? Oh. And as you can see, the imagery you can get from that, which was quite nice. And that was quite exciting. But again, the question is, this is aerial platforms. How can we make it underwater? We looked around, and was just curious if you can get any fish with kind of camera, same style. Unfortunately, this is not so much practical. Typically what you have is different other platforms that are emulating different kind of environments. What was interesting that when I met Firat, and I'll read his bio sketch. Firat is a ME second year PhD student. He received his undergrad in ME from the University of Sabancı in Istanbul, Turkey. And his ME he received from UNH. His title was The Effect of Cutting Force Model Coefficient Variability in Process Planning in Milling. Wow. And in addition to that, now Firat is in the Ocean Engineering program, second year, where he's researching with, under the advisory, under the directions from Thein, a professor in mechanical engineering, a research titled Dynamic Positioning Between Unmanned Underwater Vehicles, UUVs, Utilizing Optical Sensory Feedback. Firat also have been working in Kale Altinary Robotics and Automation in Istanbul. He has worked here with me and other people in CCOM as an instructor for the ROV Science and Application class, especially looking at optical sensors, ROV dynamics, and controls. And in addition to that, he has been working as an advisor for the last 2 years for different senior ROV, UNH ROV team projects. Firat is a member of the Ocean Engineering Society and the IEEE and MTS, the Ocean Engineering Society in IEEE and also in MTS. Last but not least, and this congratulations for Firat, last week he received the Ocean Engineering Link Foundation Fellowship. So we're all invited to dinner on his account. With that, I'll give a few words for Maywin, who is the advisor, and then we can start the presentation.
Okay, so first of all, I apologize because I'm not as funny as Shachak is. So thank you, and actually Shachak and Firat were kind enough to put me on, even though I'm not really speaking. I am Firat's research advisor, and I just want to explain what's going on right now. First of all, I'm excited because this is my first real collaboration with CCOM. So thank you, Shachak and Yuri. Okay, and we're starting research with ROVs. So we're starting with even developing undergraduate projects. So this year is our 4th year that we're doing the ROV team, and this year, with Tara's help, who's going to qualify us, we'll go to internationals in Seattle. So I'm hoping for that. And I was really happy to see Dave Lavalvo and his group put their big ROV in the tank finally, so I was happy about that. So what I want to segue into is system dynamics and control, which is our area of research. Okay, so to put it directly, if you can take any system and that changes with time, you can always describe that system with a mathematical equation. And Kevin knows all about this because I used to teach him this. Right? So you could tell everybody. Okay. He's very quiet right now. Anyway, so if you can label this system with a mathematical equation, theoretically then, if you can solve that mathematical equation, you can predict at any time what your system's going to do. And more importantly, if you can predict what your system's going to do, then you can determine what you need to put into the system so it can react the way you want it to. For example, cruise control, temperature control in your house or your car. So everything like that, as long as you can model it, we say model, with differential equations. Does everybody know differential equations? Okay, I hear a nervous chuckle. Okay, then if you can describe it with an equation, then you know everything and anything about it, ideally. But then we apply it to real systems, for example, ROV systems, and see if we can model it accurately and come out of the academic school and apply it for real. So that's where Firat comes in. All right, so I'm going to introduce Firat again. Thank you very much.
Thank you, Professor Thein and Shachak, for introduction. So first of all, before I start, I want to tell something about myself. So when I graduated from Masters in here, from Mechanical Engineering, basically my title was about milling processes, which is completely unrelated. And people naturally ask me about why did you choose, why did you make such a sharp transition? So the thing is, Professor Sheliko asked me if I was interested in such systems like ROVs and UUVs. And I literally jumped in because these systems seem pretty interesting. So here I am at my second year of PhD. So the title of my speech for today is Framework for Optical Communication Between UUVs, Unmanned Underwater Vehicles. So this is the outline for my speech today. So I'll start by very basics. I'm sure that everyone knows about UUVs, but I'm going to start with that. So what's a UUV? What's an unmanned underwater vehicle? And secondly, I'll show the proof of concept. So this study that we did before about UUVs in air. So that study was about controlling and detection, light detection in air, not underwater, consisting mostly controls. And then I'll talk about the ocean optics, which is a theoretical part of what's the light travel through underwater. What's happening to the light? What's the major effects? After that, I'll talk about my experimental setup, which we did with Shachak in underwater in the tow tank, and the results that we obtained from these experimental sets. And finish the talk by giving the conclusions and future work, also potential applications. Okay, so what's the UUV? UUV, as we all know, is unmanned underwater vehicle. And it can be grouped into two parts, which is, first one is remotely operated vehicle, ROV, and the second one is AUV, which is autonomous underwater vehicle. So if you look at what ROV looks like, which is seen on the upper right side of the slide, you see that there is a cable here. So this cable basically connects from the vehicle to the ship, and it transmits data back and forth between the ship and the vehicle, such as data such as video signals, command signals, and thus it gets the command from the ship terminal. And it's also operated by a pilot, so there has to be human interruption. There has to be someone controlling the ROV. But if you look at AUVs, they are free from tether, so there is no physical connection to anything, any ship or any other platforms. And as a result, they know where to go, so they got a pre-programmed trajectory basically, so they know where to go beforehand. And so there is no human interruption, so it's basically a more feasible system than ROVs, but it depends on the task definitely. And if you look at shape-wise, ROVs are, for ROV construction, they don't care much about the shape, because its power is coming through the ship, so it's not something to save. But if you look at AUVs, the power is a major consideration, so they need to conserve power. So the shape of the AUV is more like a torpedo, which eliminates the direct forces acting on the vehicle. And the reason why we use these vehicles is that at some depths, human cannot operate at long durations, long periods. So that's why humans rely on these vehicles in underwater tasks. So now I want to talk about UNH ROV activities. So starting with the history. So in 1980s, there was a significant search about ROVs at UNH, directed by Professor Dale Limbert. But I don't know what happened to that group, but we don't have that kind of group here. But instead, it was also possible to see their names on several control books. So they built a vehicle called EVs. So it was a big deal at the time. So now what we have is UNH ROV teams each year, every year. So these students are, most of them are from the ME department. And also there are several students coming from the electronic department, EE department and CS departments. So what they do is they build an ROV from scratch. And they go and compete first in the regional competitions, and second in the international competitions. And as Professor Thein said, it's in the Seattle this year. And when they try to build this, they try to build it in modular way so that they add several sensors. It's possible to add sensors. So it's basically a platform for further research about the ROVs. Did I miss anything, Professor Thein, about the? So what are UUVs used for? What are the applications for UUVs? So first of all, they can be used in underwater pipeline and cable inspection systems, tests like that. And also in bathymeter exploration, where they survey the depth, survey the seafloor. And also military applications, such as mine countermeasures, harbor monitoring, and anti-submarine warfare. And we can see several pictures on the slide. So the bottom line is they come in many sizes and shapes, depending on their tasks. So the possibility of using more than one UUV, more than one unmanned underwater vehicle is pretty exciting, because the tasks that are performed by doing the tasks that I mentioned in the previous slide can be done much faster if more than one vehicle is utilized. So here we see pictures of UUV fleet in operation, where we see this, basically an army of UUVs going somewhere with a specific formation. And also on the right picture, we see the same communication, where we see two AUV systems communicating with each other, and here they are in formation, and one of them is in docking stage. So the research that has been done on the UUV fleet that should perform its formation system is currently researched, but it's on simulation level. Not much experimental work has been done. But the use of multiple ROVs is not a dream. So basically NOAA uses this operation, uses this concept. So this picture shows the NOAA's Sirius camera sled. So Sirius has several sensors on it, such as HMI lights, USBL lights, and other stuff. And this one is connected, Sirius is connected to the main ROV. This is the Hercules, the yellow one. So what the function of Sirius is that it illuminates the area that the main ROV is working on. So it's decoupled from the operator control ROV, but it's also controlled by another pilot on the ship. So what we think is, if our system can add autonomy to the NOAA's Sirius system, as can be seen in Dave Laval's explanation here, he states that the Sirius can fly several meters above the main vehicle, main ROV. So we can do a leader-follower system, not necessarily side by side, but in depth offset, and apply it to this kind of a system. So to add autonomy to the systems, there has to be communication link between the vehicles. So basically what we try to do here, what's our approach? So first we determine, we have two vehicles, we start from basics, we start from scratch. We have two vehicles and we assign a leader, one leader and one follower. So basically leader is controlled by a pilot, so there is no problem in terms of control systems. It can be thought of as a light source. Okay. And the other one is the followers. So the follower doesn't know the path of the leader. So there has to be a communication link between the two. It has to know the relative position with respect to the leader. So how can this communication be performed? So first, it can be done by acoustics. And second is the optical communication. And I'm going to talk about this briefly. So what is acoustic communication? So in the most basic sense, underwater acoustic communication can be done in three different ways. Ultra short baseline, and long baseline. So on the first picture here, we see the ultra short baseline. So in ultra short baseline, there is transponder and receiver between one on the ROV and the one on the ship. So it offers a fixed accuracy between the, in terms of localizing the ROV. The other one is a short baseline. In short baseline systems on the ship, there are 4 different or multiple hydrophone arrays that are mounted on the ship, and there's a beacon pinger. So in this slide, it's shown on the seafloor, but it can be mounted on the ROV so that they can localize ROV that way too, and they also add triangulation for better accuracy than the USBL systems. The third one is the long baseline. So in long baseline, there are transponder arrays on the floor, seafloor, and they mount these arrays in such a way that in areas where the ROVs are supposed to operate or AUVs are supposed to operate. And then they are able to get their position information. So basically the bottom line is there has to be at least ultra short baseline in terms of detecting the ROV positions and communicating. So let's look at optical communication systems. Optical communication systems, in the most basic sense, again, they have some transmit electronics. So these transmit electronics basically pass through the optical elements and converted through the optical output, which is electromagnetic waves. And it has to have some kind of receiver side. So that's why we have receive electronics in there. And in receiver electronics, this incoming electromagnetic light field is received and converted into an electrical signal and further sent to process to the computer or A to D converter. And optical communication is used heavily in free space applications, space optical communications, as can be seen in the figure on the right, such as space docking systems or visual navigation in space. And it's also used in wireless optical local area networks. And another application is LiDAR, which stands for light detection and ranging, and which Shachak is working on. So in this picture, we see a robot, autonomous robot, that has a LiDAR here. So what it does is it sends several laser pulses and it can detect the range. Basically, it can detect the obstacle around it and it gives the range and the angle output with respect to the laser pulses. And the LiDAR systems can also be used in data transfer between 2 platforms. So to compare acoustics and optics, their weaknesses and strengths. So acoustic sensors have the advantage of traveling long distances. So that's a big factor. So as a result, it's good for command signals. So we can basically command the ROV at longer distances. If you look at the disadvantage of the acoustic sensors, there's a trade-off between the range and the transmission rate. So if we increase the transmission rate, the range is decreased. In the optical sensor side, the advantages are high-speed communication because of the speed of light is faster than acoustics. And there is a possibility, not maybe a reality, but a possibility for a cost-efficient system. And the disadvantage of that is the distance limitation. In underwater environment, especially, the distance will be limited. It will undergo through scattering and absorption. And that's what we chose. We chose to propose optical systems for detection of leader and follower systems. So in this slide, I'm going to give a brief overview of our study in this block diagram. So as I mentioned before, for the leader ROV, there is not much problem because it's controlled by a pilot. That's what we assume. But for the follower ROV, it has to detect the incoming light. So this is basically what we work on right now, the optical feedback part. So the idea is the follower, this is the follower block diagram, receives the light from the leader. And by the algorithms that we develop, it can convert the information into distance information. So basically it converts the light, takes the light, converts it into position information. And that position information is relative, of course, because it's between the leader and the follower. And there's a reference, we set a reference relative position between these vehicles. For example, we want to track one vehicle to other between 5 meters or 10 meters. So that's what we give as a command to the system. And we would like to track that position. So as a result, what we got from the leader follower ROV optical module as a relative position, we subtract these two and come up with an error. So that error is basically compensated by the controller And the necessary command signals are sent to the thrusters, which in turn rotate or translate the ROV. It changes ROV dynamics. And therefore, the control action is taken. So what we have done so far, so the work we have done in the IEEE Oceans 12 conference was showing a proof of concept that worked above water. So what we did was we designed a prototype array by using these components. So here we got photoresistor elements, really cheap, all of them was really cheap systems. Photoresistor elements of five consisting of 5 elements, and an LED flashlight, a microprocessor with an 8 analog to digital port. And we see our convention, axis convention here. We define our axis, x and y axis. And in the underwater experiments, by the way, we changed this x to y, to z. And what we did was, to show the proof of concept, was we got the light, and we calibrated our light measurements based on the middle photoresistor of the array. And then we developed separate models for distance detection, for x and y detection. That's what we concentrated on. So how did we detect the light, and how did we convert it into position information? It's very straightforward. So what we did was we determined the leader ROV motion type, basically, by receiving the optical input from the leader, from the light source. And then by comparing the intensity measurements at the light array, that's the photoresistor element, we could determine whether the position is horizontal or is lateral. So if it's horizontal, we use the X data model that we developed. And if it's lateral, we use 2 other models. We first detected if it's going in positive lateral or negative lateral, and then we use the prospective model based on this information. So for simulations, we had to incorporate the ROV dynamics. So basically, ROVs are nonlinear systems, 6 degrees of freedom. But here we only care about 2 degrees of freedom. And another part of the simulation is not just modeling the ROV itself, but also the light model. And for the light model, we approximated the light as a first-order Gaussian function. And we use a proportional and derivative controller. That's a PD controller that we use in the simulations. And one question maybe here is, why are you using a linear PD controller to a nonlinear system such as a ROV? And the question is, if you go back and do the math, and if you go back and incorporate the PD dynamics, the controller dynamics into equations of motion, and do the Lyapunov function analysis, it turns out to be stable in the sense of Lyapunov in the nonlinear system analysis part. And also it's used extensively in industry if you want to control the heading of the UUV and ROVs, and also depth control for the ROVs. PD controller is widely used. So what we care about is a 2D translational motion. That's what we first wanted to detect between the motions, between the vehicles. So on the figures we see blue is the leader vehicle and the follower is the red one is the follower. So what we did was we wanted the follower to follow the leader 2 meters behind, or the DX. We wanted to keep this distance basically. And we give the leader position, leader ROV, several reference points, such as 0, 1, 2, 3. And we are running these simulations under 2 conditions, with and without disturbance. So by disturbance in underwater systems, we mean current or wave. So we only use current in this case, in the simulation. So this slide shows the simulation results when there is no disturbance acting on the ROV. So it's ideal, like ocean engineering tank. So what we see here again is the leader is the blue one and the follower is the red one. And the follower is commanded to follow the leader 2 meters behind, and the leader is given these trajectories or these reference points to follow. So what we get out of this figure is that the controllers do a pretty good job. And also the optical detection system, the combination of these also is quite good. We can see that the follower can track the vehicles, the leader vehicle in here. But there's a slight deviation in here, in this part, but it can correct itself later on. So when we added current, another disturbance type to the system, to the underwater environment, what we did was the similar. So the starting point, ROV is starting at leader, ROV is starting at point A and follows these lines basically, follows these points. That's what it's supposed to do, but as we can see, it's not very successful at doing so because of the disturbance. So that's basically a problem of the controller. The optical system, we can see that it's still tracking the motion of the leader. So after the simulations, we wanted to do some algorithm testing. So how did our algorithm perform in the experimental detection? So what we did here was we set the follower ROV, which we can think about it as a light array, photoresistor array. And it was set still at a point that we determined as an origin. And we moved the light source. So, and the light source pattern is red here. So basically we dropped the shape of an H ladder. And what we see in the blue is the determined position of the leader in terms of the followers. So that's what followers is interpreting the motion of the leader. And we can see there are several discrepancies here, but still overall it's detecting it pretty nicely. So this slide shows the case where we incorporate the experimental work into our simulations. So what we did was the follower ROV set still, observed the motion of the leader basically. And then it generated its own trajectory, set of commands. So on the top part we see the X commands, X position, and the bottom part is the Y position commands. The red ones are the commands. And the black one is the position tracking for Y axis, and the blue one is the position tracking for X axis. So what can we get out of this plot? So first of all, the detection capability of the algorithm determines the control system. So for X, it determined a constant, almost like a step function. And therefore, the problem turned out to be a regulation problem, where it could easily regulate these command signals. So at point, for example, at time 50, it's commanded to go from 1.2 to 1.6. However, if you look at the Y, since the generated trajectory is not that smooth as in X case, this problem is almost like a trajectory problem where the trajectory is changing over time. So we see that the PD controller is not performing well here. It tries to track, but it's not very efficient. So the conclusions from this proof of concept work, especially on the controls. So we showed that the horizontal axis distance detection was accurate up to 5%. And the lateral axis, that's the Y axis, distance detection accuracy was worse than the X case. It jumped up to 25%. And the linear PD controllers, they are good with regulation problems without disturbance, but when we add disturbance and in the trajectory following problem, it's not performing as good. So second part of our study is the underwater part. So up to this point, we have done everything above water. Now we're going underwater with the help of Shachak. So the study goals here was to characterize the underwater light field basically. So why we're interested in the underwater light field is because we would like to determine the spectral range of the light source and the environment. And this spectral range in turn is going to give us information about what type of hardware that we want to use. Because at some wavelengths the light doesn't penetrate well enough, but other wavelengths it can do so. And also we want to develop the distance detection algorithms in underwater. And we would like to determine the boundary conditions effective on the algorithms, such as what concepts, what phenomena are effective. And also determine the effective distance between the vehicles in underwater. And another objective is to design a photo-detector array. So first of all, what kind of array are we going to use? What's the dimensions? That's the question. And by receiving the light field, by incorporating the light field, we can come up with some conclusions about this. And also locations of the independent elements on the array. So that's another goal. Where do we place these elements? So in this part, I'm going to talk about several ocean optics concepts in theoretical. So during this study, we analyzed 3 parts of curves, beam patterns. First one is the top hat. So top hat is basically an ideal case. So it's not very realistic. As we see, it's assumed to be a uniform distribution over a distance, which is not very ideal and practical to get in real time. And second one is the Gaussian, which we all know is the normal distribution. And third one is the multiple lobes, which we see when we use more than one light source. And we see the interference here.
Right, can I ask you a question about that plot?
Sure.
When you say distance there, do you mean distance or do you mean angle relative to the source?
So I mean the distance. So we are looking at the light field that is effective on a cross section. So let's say the light on here. So what I mean by distance is I determine the maximum intensity position at 0 and the distance between this where we're interested and the 0 point.
This is as observed normal to whatever the maximum response is or maximum transmission of the source, yeah?
Yeah.
Okay.
Across the a long track, perpendicular to a long track, right?
Yeah. So that's what we analyze here is the cross section. That's the line. So we are interested in the cross sectional intensity. So what the intensity looks like across this line, black line. And here we assume it's this position.
Sorry, I have another question. Do you also expect it to vary as you get off sort of a rotational axis? Do you know what I mean?
Do you mean the rotational motion?
Yeah, I mean I think what I've understood you to say is that this is sort of the view looking normal to the light source, and as you translate off to one side or another in distance, it falls off. But if the light source was rotated relative to what you have,
actually
is it the same thing or different?
Actually,
do you mind if I answer?
Yeah.
The beam that we're using here has a given solid angle of some sort. The intersection for this beam pattern and the profile you see here is when we're using only translational motion. So meaning we're looking as a cross section that is perpendicular to the main axis of the illumination. That's the main focus, but that's what you're seeing here. The focus here was only at that moment, but there is, of course, if you did a different projection at a different angle, so it doesn't matter if you move the light source of the intersection, you'll get a different beam pattern.
Okay. Thanks.
Okay, so we chose the Gaussian field as a light model, as what light is going to act like in underwater. And there are some definitions of light's beam width. So beam width is important for us because we would like to design an array concept, and we're going to illuminate the cross-sectional area. So we would like to get the intensities, and we would like to come up with a spec, basically, it is a threshold, what we use. So first one is full width half-max, FWHM. So full width half-max is defined as the points, actually, where the intensity is the half. So that's one threshold to set. Second one is the 1 over e squared. So 1 over e squared is basically extended more. So it answers the question, what if we want to get more intensity distribution? What if our full width half max interval is not enough for us to get to comment about the photoresistor outputs? So this is another method to set thresholds. And it's related to actually full width half max by 1.7 multiple. And it's also defined as 0.135 times the maximum value. So as a result, the band widens. So another important phenomenon in ocean optics and also in optics in general is the inverse square law. So inverse square law basically states that in a vacuum or in air, where we can approximate as a vacuum, the intensity of the light gets decreased by the distance. So if we go put a torch in our room, and if we move away from the light, move away from the wall, you see that the intensity at the wall is going to change. It's going to drop down. So it's basically explaining that concept. And this relation is defined as r squared. It's inversely proportional to r squared over the distance. So last but not least about ocean concepts is the Beer-Lambert law. So Beer-Lambert law basically states the turbidity level of the water. It gives us the diffuse attenuation coefficients, which is an indicator of turbidity. And it's defined by this following equation. So here, the statement is ED, intensity at the depth, is equal to intensity at reference depth times exponential relation with the KDs and Z's, the depth, the distance between them. So in traditional methods, the diffuse attenuation coefficient was calculated by Secchi's disk. So Secchi's disk was first mounted on a wall, mounted on a pole, and then released on a water. And the distance where it could not be seen anymore is basically the depth of extinction. So that's how they define the turbidity. But of course, it's very subjective to who like drops down into the water. So it's possible to get empirical measurements of diffuse attenuation coefficient, and which is especially critical in our research, because it's making us to see what kind of light, what kind of environment is going to attenuate how much of the intensity. So before moving on to the experimental work, I'll talk about the hardware a little bit. So the light sources that we used are 400 watt light source, which can be seen on the left side. And the right side we see the 50 watt light source. So these are the light sources that we used. So we had to connect 400 watt light source ballast to give ignition. And this one, 50 watt, was directly connected to 12 volts power, and it's operated like that. And it's also possible to model these light sources with respect to their wavelength with blackbody equations. So to talk about photodetectors, so what we used in our experiments was spectrometer, because we are interested in the wavelength spectral range. But now I'll talk about what we're going to use in the future, what potentially we're going to use. So the characteristics of the photodetectors are first the integration time. So integration time is basically the time that the photodetector is exposed to light. And during that stage, during that period, it collects all the light and then gives the output. And response time is basically the speed time, how fast does this photodetector respond. And it's strictly dependent on the material that the photodetector is built on. So for example, photodiodes are much faster than photoresistors. And also field of view. So field of view is a spatial characteristic. So which angle does it get the more intensity, light intensity? That's one spec. And also spectral range of the detectors. That's also important phenomenon. So we are interested in spectral range. And for example, several light detectors give several different wavelengths at which their sensitivity is different. So we would like to get more sensitivity at a visible wavelength, basically. And another thing is the dark current. Dark current is a noise associated with the photodetectors. So when you turn off all the lights, there will still be some current going on in the element. So that's not desired, so that's called dark current noise. We want this to be low. So to talk about our experiments, so we did our experiments in the tow tank, and in these pictures we can see engineering tanks and the tow tanks. So tow tank is just right behind this wall. And I know several researchers are using this tow tank a lot in this room too. So it's an ideal platform in terms of the length is long. It's a very long system. It's a very long pool. But we are interested only in this part, because we would like to get our intensities at closer range at the first place. And there is also this carrier which moves back and forth. So that's a huge advantage to us, thanks to Pete Basham, he's a PhD student. He designed and developed all the motion controllers. So let's talk about the tow tank a little bit. So the length is 37 meters, and width is 3.6 meters, and depth is 2.4 meters. So basically, we are not very constrained by the tow tank, but maybe in terms of depth, it may be a little constrained, because we can observe surface and bottom reflections at these depths, at this limited depth. And we defined our z-axis in the length of the pool, and x and y-axis are the following. X-axis is the depth, and y-axis is the lateral. So what we did here is we placed our light sources that I mentioned before, 50 watts and 400 watts, to the wall. And then we placed our light detectors at several different positions, at 5 different positions basically, from 4.5 to 8.5. And we measured the intensities and observed the intensity, how the intensities change with the distance. So this picture shows our experimental setup. So as I said, we went from 4.5 to 8.5 in z-axis. In z and x-axis, we also went from 0 to 1 meters at 0.1 meters increments. That's 10 centimeters increments to have a two-dimensional measurement, basically. And we use 450 watt light sources, and the detector that we use is a spectrometer, which is connected to a laptop. It's Ocean Optics Jazz software. And also we use a diffuser, collimator, with light detector with a collimator in the system. So here are our results. So this plot shows diffuse attenuation coefficients, and this is based on the calculation of Beer-Lambert law, basically. So how we calculated the diffuse attenuation coefficient is basically, for example, if I got the measurement at 6 meters in underwater, I got another measurement at 6 meters in air. So by doing so, I also got rid of the inverse square law addition, inverse square law contribution to the light intensities. So I did these calculations in several distances, and this is the average of them. So what we see from what we want to get from this plot is we want to attenuate the least because we want the maximum intensity. So if you look at this range from 500 nanometers to 550 nanometers, we see that the intensity, the attenuation is the least in this region. So we are getting to recognize our hardware, getting to get the specifics of hardware. So we want the hardware to be basically based on this region. So from attenuation coefficients, diffuse attenuation coefficients, we could get the percent loss. And we could also compare it with the Jarlov curves, which is an indicator of how the diffuse attenuation coefficients change with respect to different wavelengths. And if you compare, if you get these windows, if you look at the red window, and also what we got experimentally, empirically from our measurements, we see that we observe that it's falling between 2 and 3. And these define the light, the water types. So we say that the UNH tow tank water is type 2, between type 2 and 3. That's one conclusion. And another conclusion is if you look at these wavelengths, we see that after 600 nanometers, the diffuse attenuation loss increases. So we don't care about the part above 600 nanometers. So this plot shows us the experimental intensity. That's what we got in z-axis. So we placed our detectors in here, 4.5, 5.5, up to 8.5, and we got the experimental measurements at the range of 500 and 550 nanometers. So we averaged the readings at this spectral range, and we normalized them. So at the end, this is what it looks like. So we see that how much of the light intensity is lost over distances here. So if you look at 4.5, which has a normalized value of 1, at 8.5, it dropped down to 0.25. So it's lost 25% of the light intensity.
At the central beam.
What's that?
At the central beam.
At the central beam. So next step was to compare our experimental results with the theory. So blue is our experimental results, and red is the theoretical results from diffuse attenuation coefficient. So if you only got the diffuse attenuation coefficient, this is what it looks like. So it certainly doesn't match the model. It doesn't match the experimental data. So it means we forgot something. which is the inverse square law. So when we also incorporate the inverse square law, we see that it gets closer. It's a better approximation to the experimental data. So then we can get our light models. So what we use in our research, we use two different types of models, light models. First one is a Gaussian function, 1D Gaussian function, and second one is a 2D Gaussian function. So here's sigma is basically the width, the standard deviation. Mu is the center, the average. And the same for the xy. So in the 2-dimensional Gaussian function, you just have x naught and y naught, another distance term. But we assume that the light is circular. So when we assume that light is circular, x naught basically equals to y naught, and then these drop out. So to talk about our results, so what we are looking at here in our experimental setup, in this aluminum frame, we are looking at the measurements selected, taken at point 0, that's the central beam alignment, and up to 1 meter at half height. So what we did was we got this data, and we just duplicated the data in the backwards. So we assume that it's a part of a circular light assumption, light field assumption, at 4 meters with 400 watt light source. And then we fitted a model here. We fitted a Gaussian model. So we can see it's not perfectly fit, but the experimental results are basically Gaussian. It can be expressed as a Gaussian. And similarly for the 5 meters at 400 watt light source. And at 6 meters, it's similar. We got some stuff going on here. And also at 7 meters is a good fit. And 8 meters, again, we are seeing some data that needs to be worked on. So talk about our beam pattern results. So here, on the previous slides, the measurements were normalized within itself. But here we normalize based on the biggest maximum measurements. That's at 4 meters, the blue curve. And these are the distance, experimental intensity distances at several distances, measurements at several distances. And this curve, basically, the blue curve, is corresponded to the cross section at our 2D experimental measurements.
Question.
Sure.
How many measurements were taken across the
10.
beam? 10?
Yeah, across, for example, at one distance.
So and you just approximated with the straight lines in between, right?
So which straight line is?
Yes.
Yeah. So why are we interested in this beam pattern in 2D, two-dimensional? Because we would like to develop our algorithms and array designs based on that intensity information. So let's say if we get a window here and get a cross section, we can model this cross section, the experimental data, as a Gaussian. And similarly, if we take another window, we can model this again like a Gaussian too. So these are going to basically, what they are helpful for is they are giving us some information about models. So basically, can we develop a model? If yes, then we can put these models in our algorithms and develop our algorithms based on that. And another thing is that we are getting the full width half max or 1/e square measurements or our thresholds. So that we if we extend our optical module up to 1 meter, we know that we are not going to get anything. So we have to be consistent and put our light detectors on some range that we have significant intensity based on these widths, 1/e square. So discussion part, so we have, as in every experimental setup, we have several error sources. So the first one is the alignment error. So alignment errors can be analyzed in two parts basically. It's the external and internal. So as external alignment, we are talking about the distance alignment in z-axis. And internal alignment is how the beam is centered to the beam basically. So for external alignment, we don't care about much because we trust the motion, the carriage that's developed by Pete. But internal alignment is a problem, so we had to go back and repeat the experiment several times because of these alignment issues. And also the measurement errors, the measurements that we have to take by hand, so these are kind of measurement errors. And in terms of algorithm, if you do calibration errors during the data collection stage with the spectrometer, then things have potential to fall out. And also another challenge is the turbidity calculation. So for each water type, turbidity is going to change. And that has to be accounted for in the algorithms. So in terms of array design, we have to determine the beam width threshold. So what we are likely to use is 1 over E squared. And when we talk about beam dimensions and locations, this is a simple sketch showing these. So it's a one-dimensional array and two-dimensional arrays. So if you do a one-dimensional array, it's not possible to detect the motion in the other axis, in y-axis. But in two-dimensional array, we can get this information. And also the locations of the arrays, locations of these elements. Where are we going to put them? That's determined based on the Gaussian intensity measurements. And from intensity measurements, we also see several phenomena like full width half max expands, so the width doesn't stays the same at other distances. So these have to be incorporated into algorithm design and development. So what are possible applications for this research? So basically, it can be used in docking systems, underwater docking systems, where we can create optical guidance path. Apart from leader and follower formation, we can also use this in docking systems, which is shown in the figure. So if we create like optical guidance path, then the AUV can follow this light, basically. And it can also charge its batteries and send the data back to the surface for longer deployment operations. So another possible application, and also that's being currently done by Woods Hole Institute, is the wireless data transfer in underwater. So they mount optical modems in seafloor observatories to create like basic underwater internet. And they instantly get the data and send it to the surface. That's what they try to do. And they can achieve, what they want to achieve is receiving and transmitting data at higher speeds, because they want to get video feeds too. So that's another application. So for future work, detection of rotational motion, like Val's question, so this has to be done experimentally. So our work only consists of translational motions in 3 dimensions. So we will expand this to rotational motion, how the light intensity looks when we have controlled experiments. And also transmitter unit design is a future work. So we say that we are going to put light sources behind the leader, and it's going to be received by the follower. But the follower itself has also its own light source. So that may cause some interference with the leader input light source. So as a result, we can basically change what we have control over. So, and beam geometry is one of these. And laser, the width is small. Also the spectral range is too small too. So laser is also another potential to use. And also another potential is using multiple light sources and see how things look like in underwater detector side. So what we derived from this work, or from this study, so first of all, we determined our spectral range, which is a valuable information. So after this point, we're going to buy our photodiodes or whatever we want to get at this range, because we know the attenuation is the least at this range. And also we determined the range between the vehicles. So we saw that in experimental analysis, after 8.5 meters, the light at the top 10 conditions is falling to the noise background and noise level. And also detector module based on full width half max was set to 0.8 meters as the total length. So which can be mounted on one of the UNH ROV teams, ROV. That's our future goal. So I'd like to acknowledge the help and support of these people, and also the ABA department, Ocean Engineering Program at CCOM, and also the Leslie Albert Marine Endowment Program. And, Professor Chelikol is my co-advisor.
Thank you very much. Questions? Chris.
Could you show the slide where you looked at the beam attenuation and the Beer's law relationship, both what you predicted and then what you actually, yeah, this. Did you see if you could get a different K value that would fit that experimental curve, the curve with the blue points? Did you try adjusting K to see if you could get your theoretical result to model that without?
No, I just got what I got experimentally from KD. So what I'm using while generating this green curve is the average of 500 to 550 nanometers. So maybe if you change the KD value, it's going to fit better.
The reason I ask, this may be right, but something to me seems weird when you said that you also had to take into account the inverse square law. So you're basically taking this e to the negative KD, and then you're multiplying that by a 1 over d squared.
Yeah.
I'll answer that one because it's because you're used to thinking about the sunlight, and the sun is more diffuse light after it passes through the atmosphere, so you have a much uniform light. Whereas a beam, if you go, especially a torch or a flashlight, if you go beyond that, you get the dark, so the change in illumination is quite severe compared to the atmosphere itself, that is a diffuse pattern. So underwater, especially when there's no background light, you do need to take into account the inverse square law about the intensity. So that's for underwater artificial illumination, not natural sunlight illumination. But the K value that we got was correct for both the 50 watt and 400 watt. 1 month apart the experiments were done? Yeah.
Yeah.
We did it at 2 different times.
I'm still curious if you could find an experimental K that allowed you to fit that curve without, I mean, you wouldn't necessarily have to call it diffuse attenuation coefficient.
Yeah.
Just call it the
K
whatever,
system,
the
yeah.
Shachak attenuation coefficient.
That's a good
You want that
Yeah.
fits.
But that can actually improve the K accuracy.
You can fit anything through 2
Yes.
points.
Well, that's can't argue with that. Barbaros.
No,
Just waving. Okay.
I was just saying forward.
Okay. Kevin.
I have a question. You mentioned how these AUVs especially are kind of limited by their power demands and availability of power on board. Do you think you need a really high power light to achieve these ranging techniques that you're talking about? Or?
So right now what AUV no engineers use, we went them and asked them basically, and they are using 200 watt light sources.
ROVs, yeah.
For the ROVs. For the AUVs, you may determine, like, you may develop different systems where you just send pulses instead of constant.
Well, I can add to that. I don't.
Yeah.
No, I don't have anything to add. I have another question though. I was just going to comment about this slide while it was up. It seems to me that the attenuation due to the water column, the absorption in the water column seems really small compared to the 1 over r squared. Like, not negligible, but significantly small. And we were thinking about putting a laser mapping system on the AUV, and so we were debating what color of laser to use. And green is like an order of magnitude more expensive than red is. And it turns out that like the attenuation between those two over nominal ranges, it's not really that much. I mean, it is, but it's not. It's not so much that you can't buy a really powerful red laser for like a third of what you might buy just sort of a moderately powerful green laser. So it's something to think about as you go through the design process of what you choose. It might.
Do you want something working or something cheap?
Can't argue with that. Okay. No, that's a good idea. That's Tom.
First, this slide makes me want to eat licorice. The question I have is really about your concept of operation. So I guess on the front of one vehicle, you'll have an array of photodiodes, and you're basically just trying to keep the laser in the center of that array, and you have your feedback control just to. So it's not. Is it as simple as that, or
So
I'm missing the sensing part of it? I don't really get
So
what
the sensing part basically consists of the follower ROV.
Yeah.
It's gonna have a light detector module on its front, like you said. And it's gonna basically detect the light, incoming light field from the leader, where it's gonna have the light source at the bottom of its the crest. So based on the light field changes, intensity changes received by the photodetector elements, it's gonna determine if there is a motion or not.
So if it sees the light field getting over to the edge of the array, it says
It's
better
gonna-
move to keep it in the center.
Exactly.
Is it
Yeah.
just that?
So to add to that, I mean, that's why they're doing all of these light experiments, because we have to characterize the light before we can determine what level of detection that we have. So we might need an array of detectors, but we also might need an array of lights.
Also, the length of the module is dependent on the length of the ROV that you want to control too. So there are, for like UNH senior team ROVs, you made a smaller module, but the larger ROVs like we have NOAA's ROV, you made a bigger module.
So
Optical
people make interferometric light sensors when you can look at the angle, or is there some reason why you're not trying to do that? Because then you don't have to have a big, if you have a small vehicle,
Yeah.
it's so big of an array you can put on the front of that unless you're gonna try to.
Interferometric light underwater is very problematic.
Oh, I thought I was asking for Firat, but.
Yes.
That's his twin.
I have seen a system, sorry, Monica, but just following up on Tom's question, where you have two sensors with a baffle between the two, and you compare the difference between them. And so you can detect when a light source is to one side or another, even in kind of an analog kind of way. And it's binary, it's not as fine controlled as what I think you're proposing, but it's an option, I suppose.
But mention that you did look at other detectors and you found some expensive ones.
Yeah, they are most of them are expensive, so we started from cheaper, cost-efficient alternatives, basically.
But that's a good idea. Now that he's rich, we can buy the. Monica.
So I was just curious, I see for like the docking and stuff in the underwater internet, obviously why this is, like the light system would be beneficial, but in terms of like if you had a couple ROVs, or not ROVs, but AUVs, like surveying and sequence, I guess why is this more beneficial than just programming the second ROV with some kind of, so maybe the first one flies and you program it to be 5 meters off the seabed, and the second one is a little bit behind and maybe 6 or 7 meters off the seabed. Is it because you save a lot of money because you don't need a control system in the second one that's as advanced, or is that less accurate?
Well, there may be some tests that you want to change the tracking distance between them. So, for example, if you go to one side, there you have to like track pipeline, for example, that are like 10 meters apart. I'm just making up the numbers. Then you develop it to be like follow the other vehicle at 10 meters, like lateral wise. And for another side, you may want to follow it 20, like let's say 5 meters. Now basically, you have more control over what you want to follow.
Right, and you
at
can
the same
change that
deployment
during.
time. You can program the vehicle to
Yeah.
change it during the task wise.
And
Okay.
if I may add to that, a lot of times people don't realize that even if you're manually controlling an ROV, that itself involves feedback control, because what you want it to do and what it actually does is totally different.
Oh.
So to take into account the difference between the leader and the follower, so it's actively trying to follow it regardless of the situations.
Yeah, I'd imagine that with the two talking to each other, you could probably avoid potential crashes and stuff more
Yeah, that'd be
readily than
nice.
you would with just a pre-programmed.
Right.
Yeah. Okay. Great. Thanks.
It's not a dialogue.
Hmm?
It's not a dialogue.
It's not a dialogue.
The leader tells
Yeah.
Yeah.
the follower, but not the other way around.
Like a grad student advisee.
Like most students.
Chris.
So one more, when you did the estimation part of the problem, when you were calculating the distance between the leader and the follower, it looked like you were always solving that in 2D or maybe even 1D when it
Yeah, that's
seems
right.
like that's an inherently maybe 6D problem. You've got a delta X, delta Y, delta Z, and then maybe 3 Euler angles that are describing the relative orientation of the two vehicles. Have you thought about expanding that to solve for all of those parameters at once?
Well, I think these models are based on the assumption of circular light, if I got your question correctly. So these models are basically a framework for further development. So the light field, that it may not be Gaussian or circular Gaussian.
I think he was asking about the degrees of freedom. At the moment, we're working only on translational. But are you going to look into rotational?
Oh yeah, that's the plan. That's the future work. So we're going to need to do the experiments for that too, and base our algorithms based on the a priori data, basically.
So
Is that-
eventually, we would like a full 6D of whether Euler angle quaternions, but we would like to incorporate attitude as well as translation.
Maybe
Yeah.
4.
Oh, yeah, I was wondering about how these sort of systems deal with light noise. Like a jelly or something, some sort of, any light noise, I guess, that you might find in the ocean.
So are you asking about like measurement noise, like the inherent noise, or like interruption?
Like a source that you're not trying to track, that the follower
Like,
senses and maybe starts following because
so
what's in the band that
For
you're.
instance.
yeah, so that's a big problem actually, but that's why we have these filters. And also if there's like another incoming light field,
Mhm.
we can like specify, we can set our wavelengths of light detectors based on like, detect only 500 nanometers to 510 nanometers, and reject everything above that besides that.
And the solid angle, so masking from the sides.
And the size for the solid angle too. And if something coming from the sides, then you can mount photo detectors too.
And I'm sorry to keep interjecting. To add on to that, this is a Firat's PhD thesis. There's another, hopefully, thesis that uses Firat's research. There's an area within systems and controls that specifically is estimation. So if you had a jellyfish or another light source, that would hopefully be robust enough to say, okay, just kidding, that's not what you're really looking at, this is what you're really looking at. So hopefully that will marriage the two together.
But that's something that needs to be considered as a future work, because like you said, sunlight is also quite effective and can distort the result measurements too.
Or multiple light sources from one system.
Yeah.
Okay, so by that, thank you very much.